Have you ever wondered what really separates, say, a solid block of ice from the water in a river, or the steam coming from a kettle? I mean, it's all the same stuff, right? H2O. But they exist in completely different worlds. Well, the secret isn't what they're made of. It's all about the hidden, energetic dance of the tiny particles inside.
Okay, so let's get right into it. It really boils down to something this simple. When you add heat, you're just pumping those particles full of kinetic energy. They start vibrating like crazy, eventually breaking the forces holding them together and moving farther apart. And just like that, you go from a solid to a liquid to a gas. Now, if you take that energy away by cooling it down, the exact opposite happens. The particles slow down, those attractive forces grab hold again, and they start lining up all nice and neat. It's all just a game of energy. So, where do we kick off this journey? We're going to start with gases. Now, you might think they're the most chaotic, random state of matter, and you'd be right. But here's the thing. That actually makes them the simplest to understand. Why? Because under the right conditions, they follow a really beautiful, clear set of rules. To get a handle on gases, scientists came up with this brilliant model called an ideal gas. So in this perfect little world, gas particles are just tiny little dots zipping around randomly. And when they hit each other, they bounce off perfectly, kind of like billiard balls, without losing any energy. And here's the most important part. They don't attract or repel each other at all. In this model, temperature isn't some weird abstract thing. It's literally just a measure of how fast, on average, these particles are moving. Now, this model gives us some really powerful and, honestly, common sense rules. First up, we've got Boyle's law. This one just makes sense, right? If you take a bunch of gas in a container and you squeeze it into half the space, well, those particles are going to be hitting the walls twice as often. That's double the pressure. So less volume means more pressure. It's a perfect inverse relationship.
And this graph, he just lays it all out for us perfectly. You can see right here, as the pressure on the bottom axis goes up, the volume on the side axis comes down in this beautifully predictable curve. That's Boyle's law right there in picture form.
Okay, so what happens if we crank up the heat? Well, the particles start moving a whole lot faster. Now, if the container can't expand, say it's a rigid tank, they're just going to slam into the walls harder and more often. That increases the pressure. That's Gay-Lussac's law. But if the container can expand, like a balloon, those faster particles will push the walls outward, making the volume bigger. And that's Charles's law. See the pattern? In both cases, more heat equals more action.
Now, what's so cool about this slide is the graph for Charles's law. Look at that. It's a perfectly straight line. This tells us that the relationship between temperature and volume is direct and linear. For every single degree you heat a gas, it expands by a predictable amount. It's just beautifully simple. So we've got all these separate rules for pressure and for volume and for temperature. What if we could just roll them all into one? Well, we can, and we get this, the ideal gas equation. PV equals nRT. This is the master formula, the one that connects all the dots. It tells us that pressure times volume is equal to N, that's how much gas you have, times R, which is just a special number called the gas constant, times the temperature. It's one elegant equation to describe the state of any ideal gas.
But, and this is a big but, that ideal gas we've been talking about, it's a perfect model. It's not actually real. It doesn't truly exist in the real world. So what happens when our neat and tidy rules come face to face with messy reality? So here's the fundamental difference. Our ideal gas, over on the left, assumes the particles are just points in space with zero attraction for each other. But a real gas, on the right, well, its particles actually take up a tiny bit of space, and, especially when you get them close together, they do feel these small forces of attraction to one another.
And here is the proof. This is where the rubber meets the road. See that dotted line? That's our ideal gas, behaving perfectly. But look at the solid lines. For real gases like nitrogen and CO2, they start to stray from the path. And why is that? Well, when you crank up the pressure or you drop the temperature, you force those particles really close together. And all of a sudden, their actual volume and those little attractions between them start to matter, and they stop obeying those simple, ideal rules.
All right, let's hit the brakes on the wild world of gases. We're going to cool things way, way down now and step into the highly organized, predictable, and structured world of solids.
You know, the absolute key feature of most solids is order, and that order has a name, the crystal lattice. You should think of it like the microscopic blueprint or the scaffolding for the material.
It's this perfectly repeating three-dimensional pattern of particles, and it dictates the solid's entire character.
So first up, we've got the giant ionic lattice. The textbook example? Table salt. What you're looking at here is this super rigid grid of positive sodium ions and negative chloride ions, and they are locked tightly in place by some powerful electrostatic forces. This crazy strong attraction is what makes salt crystals hard. It gives them high melting points, and it's also why they're brittle. If you hit them, the layers shift. The positive ions line up with positive ions, and poof, the whole thing shatters.
Okay, let's switch gears to a totally different structure, the metallic lattice. Here, you've got positive metal ions all lined up in a lattice, but they're surrounded by this free-flowing sea of electrons. Now, these electrons are called delocalized, which is a fancy way of saying they don't belong to any one atom. They belong to the whole structure. This electron sea, it acts like a flexible glue. It's why metals can bend without breaking, and it's exactly why they're such great conductors of electricity. Those free electrons are just ready to get up and move.
And now for the heavyweight champion of solids, the giant covalent lattice. Just think of diamond. In this thing, every single atom is connected to its neighbors through incredibly strong covalent bonds, basically forming one giant single molecule. There are no weak links here. To melt a diamond, you have to actually break these powerful bonds, which takes an enormous amount of energy. And that's what makes these things extremely hard with sky-high melting points.
So let's just pull this all together for a second. This table sums it up perfectly. Whether you're talking about ions held together by electrostatic forces, or atoms held by covalent bonds, or metal ions chilling in a sea of electrons, the type of particle and the force between them directly determines what the material is like. And notice how all three of these giant structures have high melting points? That is no accident. It takes a ton of energy to break up these huge, strong networks.
You know, to really drive this point home, how absolutely critical structure is, we only need to look at one element, carbon. It is the ultimate case study in how the arrangement of atoms doesn't just change a property a little bit, it creates a completely different reality.
Just look at this. On the left, you've got graphite, the soft, gray stuff in your pencil. On the right, diamond, the hardest natural substance known to man. And get this, they are both made of the exact same thing, 100% pure carbon atoms. The only difference is the blueprint, the way those atoms are connected to each other.
And that one difference changes everything. Graphite's atoms are arranged in these flat sheets that are only weakly held together, so they slide right off, which is what makes it so soft. It also has free electrons between those sheets, which is why it can actually conduct electricity. Diamond, on the other hand, is a whole different story. Every carbon atom is bonded tightly to 4 others in this rigid 3D network. This makes it incredibly hard, and it locks up all the electrons, making it an electrical insulator.
So what's the bottom line here? It's this: structure is destiny. I mean, this single idea is one of the most foundational concepts in all of science. The properties we see and feel in the world around us emerge directly from the invisible architecture of atoms.
And this idea has never been more important than it is today. We're not just stuck with graphite and diamond anymore. Scientists can now rearrange carbon atoms into incredible new forms, like hollow spheres called fullerenes, tiny little tubes, and graphene, which is a sheet of carbon that's only 1 atom thick and is ridiculously strong. It all leaves us with this incredible question. If simply rearranging atoms can turn soft into hard, what amazing new worlds and technologies are we going to build now that we can design them one atom at a time?